Hello everyone, today we'll study subspace. First of all, let me show you some common vector space. Then I'll show you the subspace of this vector space. Rn under the standard operation is a vector space. R infinity represents the set of all infinite sequence. R infinity is also a vector space under the standard operations. MMN represents the set of all m by n matrices. And MMN under the standard matrix operation is also a vector space. F from negative infinity to infinity. This symbol represents the set of all real valued functions. Real valued function means it's a function whose codomain is the set of all real numbers. That means the output of the function is always a real number. For real valued function, the output of the function is always a real number. Here, f from negative infinity to infinity represents the set of all real valued functions, which are well defined on the interval from negative infinity to infinity. And we know that f from negative infinity to infinity under the standard function operation is also a vector space. So those are some common vector space. We can verify all 10 axioms to show that they are all vector space, and those are some common vector space. Next, let me introduce subspace. Let V be a vector space, and let W be a subset of V. If W itself is also a vector space under the same operations defined on V, then W is called a subspace of V. So, if W is a subset of V, and W itself is also a vector space, then we say W is a subspace of V. So, if W is a subset of V, in order to show W is a vector space, we must show that W satisfies all 10 axioms of vector space. So, in order to show W is a subspace of V, we must show that W also satisfies these 10 axioms. But if we try to show all 10 axioms, it may be too much work. There's a simpler way to check W is a vector space. There's a simpler way to show W is a subspace of V. Let's look at the following theorem. The following theorem says that W be a subset of V. Then W is a subspace of V if the following conditions are satisfied. So that's a simpler way than checking all 10 axioms. Comparing to checking all 10 axioms, this is a simpler way to show W is a subspace of V. So if these three conditions are satisfied, then W is a subspace of V. Condition 0 show that W is not empty. W is not empty set. Condition 1 says, for all U and V in W, U plus V also belong to W. That means W is closed under vector addition. This is the same as axiom 1. In vector space. Condition 2 says, for all scalar K, and for all U in W, Ku belong to W. That means W is closed under scalar multiplication. That's the same as axiom 6. The second condition here is the same as axiom 6. So, in order to show W is a subspace of V, we must show that W is not empty. W is closed under vector addition, and W is closed under scalar multiplication. Now let's prove this theorem. In order to prove this theorem, we try to show that if W satisfies these three conditions, then it satisfies all 10 axioms. We try to prove that if W satisfies these three conditions, then it must satisfy all 10 axioms. So, according to the definition here, since condition 1 is the same as axiom 1, condition 2 is the same as axiom 6. So by the given condition, we know that axiom 1 and axiom 6, they are automatically satisfied. Axiom 1 is the same as condition 1. So it's satisfied. Axiom 6 is the same as condition 2, so it's also satisfied. Axiom 6 is the same as condition 2. So it's also satisfied. Now, axioms 2, 3, 7, 8, 9, 10 are true for all vectors in V. Since W is a subset of V, then for all vectors in W, it satisfies axioms 2, 3, 7, 8, 9, 10 automatically. So axioms 2, 3, 7, 8, 9, 10 are directly inherited from vector space V. So axioms 2, 3, 7, 8, 9, 10 are directly inherited from vector space V. Since W is a subset of V. What's left is axiom 4 and 5. What's left is axiom 4 and 5. So in axiom 4, we try to show that there's a zero vector in W. In axiom 5, we try to show that for all vector in W, there's an additive inverse. So what's left is axiom 4 and 5. Now, since W is not empty, then there exists a vector U in W. Since W is not empty, there exists a vector U in W. Then by condition 2, KU belongs to W for all scalar K. By condition 2, KU belongs to W for all scalar K. If I let K equal to 0, then 0U equal to 0 vector. From last class, we know that scalar 0 times any vector U is vector 0. If K is 0, then KU is 0U. Equal to 0 vector belong to W. So axiom 4 is satisfied. Since 0 belongs to W, axiom 4 is satisfied. If I let K equal to -1, then ku equal to -1u. And from last class we know that -1u, -1 times u is the same as -u. -1 times u is the same as -u. That belongs to vector w. So axiom phi is satisfied. For all vector u, there exists an additive inverse. Axiom phi is satisfied. Since all 10 axioms are satisfied, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since all 10 axioms are satisfied, W is a vector space under the same operation on V. Therefore, W is a vector space under the same operation on V. Since W is a subset of V and W itself is a vector space, then W is subspace of V. Hence, W is a subspace of V. Next, let's create an example. Let W be the set of SYG in R3 such that G equal to 2x minus 3y. Show that W is a subspace of R3. So, in order to show W is a subspace of R3, we try to show that W satisfies these three conditions. If all three conditions are satisfied, then W is a subspace of R3 under the same operations. Let's prove it. So first step, for condition 0, we try to show that W is not empty. Let me try to show that there is some vector in W. So find a vector in W. We know that if I let S be 1, if I let Y be 1, then Z is -1. So the U equal to 1, 1, -1. The U equal to 1, 1, -1. Pick any example. If I let S equal to 1, Y equal to 1, then Z is -1. The U equal to 1, 1, -1. Then 2x minus 3y. In this vector U here, 1 represents x, second one represents y, -1 represents z. So 2x minus 3y equal to 2 times 1 minus 3 times 1, which is -1. -1 equal to z. Since vector U satisfies this condition here, we can say vector U belongs to W. So vector U belongs to W. If there's vector belongs to W, then W is not empty. If there's something belongs to W, W is not empty. So condition 0 is satisfied. Condition 1, we try to show that W is closed under addition. The U equal to U1, U2, U3, V equal to V1, V2, V3 belong to W. Then both vector U and V satisfy this condition. That means U3 equal to 2 times U1 minus 3 times U2. U1 represents X, U2 represents Y, U3 represents Z. So U3 equal to 2 times U1 minus 3 U2. And same thing works for vector v. V also satisfies this condition. So v3 equal to 2 times v1 minus 3 times v2. If I add the vectors u plus v, if I add the vectors under standard operation u plus v, we add the corresponding entries, add the corresponding components, I get u1 plus v1, comma u2 plus v2, comma u3 plus v3. That's a new vector. This is a new vector. Now, here u1 plus v1 represent x, u2 plus v2 represent y, u3 plus v3 represent z. I'm going to check if they satisfy this condition. 2x minus 3y equal to 2 times u1 plus v1. This is x. Minus 3y. Y is this. u2 plus v2. That can be rewritten as 2 times u1 plus 2 times v1 minus 3 times u2 minus 3 times v2. If I put all the u's together, I get 2u1 minus 3u2 plus 2v1 minus 3v2. We know that 2u1 minus 3u2 is u3. 2v1 minus 3v2 is v3. So here we get u3 plus v3, and we know that u3 plus v3 is z. That's syz. u3 plus v3 is z. So we have 2x minus 3y equal to z. So vector u plus v satisfies the condition here. Hence, u plus v belong to w. U plus v belongs to w. That means w is closed under vector addition. That means w is closed under vector addition. So assume condition 1 is satisfied. It satisfies condition 1. Next, let's check condition 2. For condition 2, the u equal to u1, u2, u3 belong to w. Then it satisfies the condition that u3 equal to 2u1 minus 3u2. Here u1 represents x, u2 represents y, u3 represents z. So z equal to 2x minus 3y. Since vector u belongs to w, it must satisfy this condition here. Next, let k be a scalar. Let k be a scalar. K times u, under the standard operation, k times u. When we have a scalar times a vector, we multiply the scalar to each component in the vector. I get ku1, comma ku2, comma ku3. Now, in this vector here, that's a new vector. In this vector here, ku1 represents x, ku2 represents y, ku3 represents z. So I try to check if this vector satisfies the condition that z equal to 2x minus 3y. Let's check the condition. 2x minus 3y equal to 2 times ku1 minus 3 times ku2. Those are real numbers. Those are real numbers, so I can pull out k. If I pull out k, I get 2u1 minus 3u2. We know that 2u1 minus 3u2 is u3. So I get ku3. This vector here, first component represents x, second component represents y, third component represents Z. So here KU3 is Z. So we have 2x minus 3y equal to Z. If vector KU satisfies the condition that 2x minus 3y equal to Z, then we say vector KU belongs to W. Hence, KU belongs to W. So W is closed under scalar multiplication. Since condition 0, 1, and 2 are all satisfied, then we say W is a subspace of R3 under the same operation. Therefore, W is a subspace of R3 under the same operations. Next example, let W be the set of 3 by 3 matrix A, such that trace of matrix A is 0. Show that W is a subspace of M33. So same thing, in order to show W is a subspace of M33, we must show that W satisfies condition 0, 1, and 2. Let's prove it. First of all, let's try to show that W is not empty. So try to show that something belongs to the set. So first of all, give an example. Let's satisfy this condition. Let A be the set of 1, 0, 0, 0, 1, 0, 0, 0, negative 2. Then trace of A is 1 plus 1 plus negative 2, which is 0. So this matrix A belongs to W. Hence W is not empty. That's condition 0. Next, for condition 1, we try to show that W is closed under vector addition, which is the same as matrix addition. So let A be a 3 by 3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. Let B be a 3 by 3 matrix, B11, B12, B13, B21, B22, B23, B31, B32, B33. Let matrix A and B belongs to W. Let matrix A and B belongs to W. Then both matrix A and B satisfy this condition. Then trace of A is 0 and trace of B is 0. Now, if I add a matrix, matrix A plus B, when I add a matrix, by matrix addition, we add the corresponding entries. I get A11 plus B11, A12 plus B12, A13 plus B13, A21 plus B21, A22 plus B22, A23 plus B23, A31 plus B31, A32 plus B32, A33 plus B33. That's matrix A plus B. Now let's check the condition. Let's check this condition, trace of the matrix A plus B. trace of matrix A plus B. That's the sum of the main diagonal. I get A11 plus B11 plus A22 plus B22 plus A33 plus B33. If I group all A's together, I get A11 plus A22 plus A33. If I group all B's together, I get B11 plus B22 plus B33. A11 plus A22 plus A33, that's trace of A. B11 plus B22 plus B33, that's trace of B. So trace of A plus B equal to trace of A plus trace of B. And we know that trace of A is 0. Trace of B is also 0. We get 0 plus 0 equal to 0. So trace of A plus B is 0. That means this vector A plus B satisfies this condition here. So matrix A plus B belongs to W. That means W is closed under vector addition. If A plus B satisfies the condition that trace of A plus B is 0, that means this vector A plus B belongs to W. So W is closed under vector addition. Next, let's try to check that W is closed under scalar multiplication. Let A be the matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Then let A belongs to W. Then trace of A is 0. Let K be a scalar. If I multiply KA using a standard matrix multiplication, a scalar times we'll have a scalar times a matrix. We distribute a scalar to each entries in the matrix. I get KA11, KA12, KA13, KA21, KA22, KA23, KA31, KA32, KA33. Then for trace of KA, we add all entries in the main diagonal. Add all entries in the main diagonal. I get KA11 plus KA22 plus KA33. Here, K is a common factor. I can pull out K. If I pull out K, I get A11 plus A22 plus A33. A11 plus A22 plus A33, that's trace of A. So I get K times trace of A. We know that trace of A is 0. We get K times 0, which is 0. So trace of Ka is 0. If trace of Ka is 0, it satisfies this condition here. That means Ka belongs to W. So W is closed under scalar multiplication. Since W is not empty, closed under addition, closed under scalar multiplication, then W is a subspace of M33 under the same operations. Therefore, W is a subspace of M33 under the same operations. Next example, let W be the set of function f such that f of x is x times f prime of x. Show that W is a vector space of f from net infinity to infinity. Here, capital F represents the set of all real-valued functions which are well-defined from net infinity to infinity. We try to show that W is a subspace of f. So same thing. In order to show W is a subspace of f, we must show that W is not NP. W is closed under vector addition. W is closed under scalar multiplication. Let's prove it. Check condition 0 first. We first will try to show that W is not NP. So try to find a function that satisfies this condition here. Let f of x equal to x. Then f prime of x, if we take derivative, we get 1. So f of x is x, which is the same as x times f prime of x. So f of x is the same as x times f prime of x. Hence, so this f belongs to W. Hence W is not NP. First, I find a function that belongs to W. That means W is not NP. So condition 0 is satisfied. Condition 1, we try to show that W is closed under vector addition. Let f and g, let function f and g belong to W. Then both function f and g satisfy the condition. Then f of x equal to x times f prime of x, and g of x equal to x times g prime of x. We try to show that function f is closed under vector addition. Let h equal to f plus g. Let function h equal to f plus g. Then h of x equal to f plus g of x. By the standard function operation, f plus g of x is equal to f of x plus g of x. We know that f of x is x times f prime of x. G of x is x times g prime of x. Then I can factor h out. I can factor s out. I get f prime of x plus g prime of x. Then by first semester calculus, we know that f prime of x plus g prime of x is the same as f of x plus g of x prime. F of x plus g of x, that's the same as f plus g of x prime. And we know that function f plus function g is function h. We have h prime of x. Since function h satisfies this condition here, h belongs to W. Therefore, f plus g belongs to W. Hence, f plus g belongs to W. So W is closed under vector addition. Next, we try to show that W is closed under scalar multiplication. let function f belong to W. Then f of x equal to x times f prime of x. Let k be a scalar. Next, let h be k times f. Let function h be k times f. We try to show that h belongs to W. Then h of x equal to kf of x. H of x equal to kf of x. By the standard function operation, kf of x is the same as k times f of x. By the standard function operation, kf of x is the same as k times f of x. F of x is x times f prime of x. Then I can pull out x. If I pull out x, move k inside, they're all real numbers. K, x, f prime of x, they're all real numbers. I can move x outside and bring k inside. I have x times k times f prime of x. Then, by the first method calculus, k f prime of x can be rewritten as k times f of x prime. K f prime of x can be rewritten as k times f of x prime. By the first method calculus, k times f prime of x can be rewritten as k times f of x prime. That's the same as k times x times kf of x prime. And we know that kf, function kf is h. So that equal to x times h prime of x times h prime of x. So h of x equal to x times h prime of x. That means it satisfies this condition here. Function h belongs to W. Hence, kf belongs to W. So W is closed under scalar multiplication. Since W is not empty, it's closed under vector addition, and it's closed under scalar multiplication. Then W must be a subspace of F from net infinity to infinity. Therefore, W is a subspace of F under the same function operation. That complete the proof. Next, let me show you some subspace of capital F. Here, capital F from net infinity to infinity represent a set of all real valued functions, which is well defined on the interval from net infinity to infinity. Those are all subsets of capital F. Here, C from net infinity to infinity represent the set of all functions, which is continuous on the interval from net infinity to infinity. The set of all functions continues on the set from net infinity to infinity. Cn from net infinity to infinity is the set of all functions whose n derivatives are continuous on the interval from net infinity to infinity. C infinity from net infinity to infinity represent the set of all functions whose all derivatives are continuous. P sub n represent the set of all polynomials whose degree are less than or equal to n. P sub infinity represent the set of all finite and infinite polynomials. P infinity represent the set of all finite and infinite polynomials. if we know calculus, this is also called power series. Finite or infinite polynomials, they are also called power series. So P infinity is the set of all finite and infinite polynomials. The polynomial whose degree is less than or equal to infinity is the set of all finite or infinite polynomials. All above sets are subspace of F. All above sets, they are subspace of F from negative infinity to infinity. Indeed, Pn is a subset of P infinity. All polynomials whose degree is less or equal to n is a subset of all polynomials, all finite or infinite polynomials. So Pn is a subset of P infinity. P infinity is a subset of C infinity from net infinity to infinity. P infinity, all finite or infinite polynomial is always whose derivative is always continuous. If we keep taking derivative for any polynomial, its derivative is always continuous. So P infinity is a subset of C infinity from net infinity to infinity. And C infinity from net infinity to infinity is a subset of Cn from net infinity to infinity. If a function whose all derivatives are continuous, then its n derivative must also be continuous. If its all derivatives are continuous, then its n derivative must also be continuous. So if a function satisfies this condition, it must also satisfy this condition. If all its derivatives are continuous, then its n derivative must be continuous. And similarly, Cn from net infinity to infinity is a subset of C from infinity to infinity. For any function, if its n derivatives are continuous, the function itself must be continuous. For any function, if its n derivative is continuous, the function itself must be continuous. And same thing, if a function is continuous, it must be well defined. If a function is continuous from net infinity to infinity, it must be well defined from net infinity to infinity. So C net infinity to infinity is a subset of F net infinity to infinity. So those are their relationships. And they are all subspace. They are all subspace. Next, let me show you a theorem. Let V be a vector space. If W1 and W2 are subspace of V, then W1 intersection W2 is also a subspace of V. This theorem says if two sets are subspace of V, then their intersection is also a subspace of V. Let's prove it. First of all, let W be the intersection of W1 intersection W2. We try to show that W is a subspace of V. According to the previous theorem, in order to show W is a subspace of V, we need to show that W is non-empty. W is closed under vector addition, and W is closed under scalar multiplication. So first of all, let's show that W is non-empty. Since W1 and W2 are subspace in V, that means W1 and W2, they are also vector space. Since they are subspace of V, they are also vector space. Then by axiom 4, 0 belongs to W1 and W2. That's axiom 4. Since W1 and W2 they are subspace of V, which means they are also vector space. Then by axiom 4, we know that 0 vector belongs to W1 and 0 vector belongs to W2. Hence, 0 vector belongs to W1 intersection W2. Since W equal to W1 intersection W2, we can say that 0 belongs to W. So W is not empty. If there's something belong to W, W is not empty. That's condition 0. Next, verify condition 1. Try to show that W is closed under vector addition. Let vector u, v belong to W. Let vector u and v belong to W. Since W is the intersection of W1 and W2, since W is the intersection of W1 and W2, then both u and v belongs to W1 and W2. Since W is the intersection of W1 and W2, then both u and v belongs to W1 and W2. Then since W1 and W2 they are subspace, which means they are also vector space. If they are vector space by axiom 1, they are closed under vector addition. So u plus v belongs to W1 and u plus v belongs to W2. Hence, u plus v belongs to W1 intersection W2, which is W. So W is closed under vector addition. Next, try to show that W is closed under scalar multiplication. Let u belongs to W and let k be a scalar. We try to show that k times u also belongs to W. Since W equal to W1 intersection W2, then u belong to W1 and u belong to W2. Since W1 W2 they are subspace of V, which means they are also vector space. Since W1 W2 they are vector space, then by axiom 6, Ku belongs to W1 and Ku belongs to W2. So by axiom 6, Ku belongs to W1, Ku belongs to W2. Hence, Ku belongs to the intersection W1 intersection W2, which is equal to W. So Ku belongs to W, which means W is closed under scalar multiplication. Since it satisfies these three conditions, W is a subspace of V. That's the proof of this theorem. This theorem says, for any two subspace of V, their intersection is also a subspace of V. And in general, this theorem is true for n subspace. Suppose we have W1, W2 up to Wn. If they are all subspace of V, then the intersection is also a subspace of V. The proof is very similar. Next theorem. Let A be an n by n matrix. Then the solution set of the homogeneous linear system AES equal to 0 is a subspace of Rn. The solution set, it means the set of all solutions. The solution set means the set of all solutions of the homogeneous linear system AES equal to 0. Here, A is a m by m matrix. X is a column vector. In order to multiply A and X must be a m by 1 column vector. In order to multiply A and X must be a m by 1 column vector. Therefore, each X is an element in Rn. Since X is an m by 1 column vector, each X is an element in Rn. So, the set of all solutions form a subset in Rn. This theorem says the set of all solutions is actually a subspace of Rn. Let's prove it. First of all, let W be the solution set of the homogeneous linear system AES equal to 0. Let W be the solution set of the homogeneous linear system AES equal to 0. Then W can be written as the set of all X in Rn such that AES equal to 0. For every column vector, if we satisfy this equation AES equal to 0, then it belongs to W. We try to show that W is a subspace of Rn, which means we need to show that W is not NP. W is closed under vector addition, and W is closed under scalar multiplication. Let's first of all show that W is not NP. Let 0 vector be an element in Rn. Let 0 vector in Rn. Then A times 0 is 0. A times 0 is 0. Since A times 0 equal to 0, that means 0 satisfies the equation AES equal to 0. Since A times 0 equal to 0, that means 0 satisfies this equation AES equal to 0. If I plug in 0, I get 0. It means 0 satisfies this equation. So 0 belongs to W. Hence W is not NP. Next, we have to show that W is closed under vector addition. The U and V belong to W. The U and V belong to W. Since U and V belong to W, they must both satisfy this equation. Then we have AU equal to 0 and AV equal to 0. Both U and V satisfy this equation. That means if I plug in U, I get 0. If I plug in V, I also get 0. Next, to show that U plus V, their sum, U plus V, also belongs to W. Let's consider this. A times U plus V. A times U plus V equal to AU. By matrix distribution, I get AU plus AV. Since AU is 0, AV is also 0. 0 plus 0 is 0. That means A times U plus V is 0. If U plus V satisfies this equation, that means U plus V belongs to W. Here, since A times this vector U plus V equal to 0, that means this vector U plus V satisfies this equation AES equal to 0. Therefore, the vector U plus V belongs to W. So W is closed under vector addition. Next, we have to show that W is closed under scalar multiplication, then U belongs to W, which means AU equal to 0. Then U belongs to W, which means AU equal to 0. Let K be a scalar. We try to show that KU also belongs to W. So if I take A times KU, A and U, they are matrices. K is a scalar. I can pull out scalar. That is A times K times AU. Since AU is 0, I get K times 0. And K times 0 is 0. K times the 0 vector is a 0 vector. Which means A times this vector KU equal to 0. If A times KU equal to 0, that means KU satisfies this equation. If A times KU equal to 0, that means this vector KU satisfies this equation. Therefore, KU belongs to W. Therefore, W is closed under scalar multiplication. Since W is not empty, W is closed under vector addition and scalar multiplication. Therefore, W is a subspace of Rn. Therefore, W is a subspace of Rn. Let's complete the proof. Next, let me introduce linear combination. Let V be a vector space, and let V1, V2, Vn, and W be vectors in V. If W equal to K1 times V1 plus K2 times V2 plus Kn times Vn for some scalars K1, K2, Kn, then W is called a linear combination of V1, V2, Vn. And the scalars K1, K2, Kn, they are called the coefficients of the linear combination. So, if W can be written as K1, V1 plus K2, V2 plus Kn, Vn, then W is called a linear combination of V1, V2, Vn. And the scalars K1, K2, Kn, they are called a coefficient of the linear combination. Next, let's look at some examples. First example, let V1 be 1, 1, 1, let V2 be 1, 2, 3, let V3 be 0, -1, 2, and let W be -1, 2, and -3. Let V1, V2, V3, W be vectors in R3. Determine whether W can be written as a linear combination of V1, V2, V3. So we try to determine whether W can be written as K1 times V1 plus K2 times V2 plus K3 times V3. If we can find such scalars K1, K2, K3, then we say W can be written as a linear combination of V1, V2, V3. Otherwise, if we cannot find such scalars K1, K2, K3, then we say W cannot be written as a linear combination of V1, V2, V3. Here, W is -1, 2, -3. We don't know K1, K2, K3. V1 is 1, 1, 1. V2 is 1, 2, 3. And V3 is 0, -1, and 2. We try to find K1, K2, and K3. Here, on the right side, let's multiply and add a vector together on the right side. Let's first of all multiply and add a vector together. I have K1, K1, K1 plus K2, 2K2, 3K2. That's scalar multiplication plus 0, comma, negative k3, comma, 2k3. Here on the right side, we first of all do scalar multiplication. Next, we do vector addition. When we add the vectors, add the corresponding components, we get k1 plus k2, k1 plus 2k2 minus k3. The third component is k1 plus 3k3 plus 2k3 that's 3k2 here. k1 plus 3k2 plus 2k3. And that equal to negative 1, 2, negative 3. Negative 1, 2, negative 3. Next, by matching the components, we have an equation k1 plus k2 equal to negative 1. k1 plus 2k2 minus k3 equal to 2. k1 plus 3k2 plus 2k3 equal to negative 3. By matching the component, first component equal to the first component, second component equal to the second component, third component equal to the third component, we get these three equations. If we write these three equations as a matrices, if we write these three equations as an augmented matrix, we have 1, 1, 0, negative 1, 1, 2, negative 1, 2, 1, 3, 2, negative 3. If we write this system of equations as an augmented matrix, that's what I get here. If we observe this matrix, we can see that the first column of the matrix is exactly the same as V1. The second column is exactly the same as V2. The third column is exactly the same as V3. And the last column is exactly the same as W. So as a shortcut, in general, if we try to find scalars K1, K2, K3, we can put V1 in the first column, V2 in the second column, and V3 in the third column, then put W in the last column. As a shortcut, we can put vectors V1, V2, V3 in the first three columns, and put W in the last column. Next, we try to solve this system of equations for K1, K2, K3. Try to solve the system of equations for K1, K2, K3. Here we can use Gauss-Jordan elimination for these matrices. We can use Gauss-Jordan elimination. Let me copy the matrix, put it here. First column, 1, 1, 1. Second column, 1, 2, 3. Third column, 0, negative 1, 2. And the W is negative 1, 2, and negative 3. Use Gauss-Jordan elimination, solve for K1, K2, K3. I can first of all multiply first row by negative 1, add it to the second row. I get 1, 1, 0, negative 1, 0, 1, negative 1. 1 plus 2 is 3. Next, I can multiply first row by negative 1, add it to the third row. I get 0, 2, 2, negative 2. Next, in the second row, we have a leading one here. Next, I can multiply second row by negative 1, add it to the first row. I get 1, 0, 1. negative 4. Next, I can multiply second row by negative 2, add it to the third row. I get 0 here, 4 here. Negative 6 plus negative 2 is negative 8. Next, in the third row, try to make leading one here. I can divide third row by 4. I get 1, 0, 1, negative 4 in the first row, 0, 1, negative 1, 3 in the second row, 0, 0, 1, and negative 2 in the last row. Next, I can multiply the third row by negative 1, add it to the first row. I get 1, 0, 0. Negative 1 times negative 2 is 2. 2 plus negative 4 is negative 2. Next, I can directly add the third row to the second row. I get 0, 1, 0, 1, which means K1 equal to negative 2, K2 equal to 1, K3 equal to negative 2. If we can find such K1, K2, K3, which make W equal to K1 V1 plus K2 V2 plus K3 V3, that means W can be written as a linear combination of V1, V2, V3. So W equal to negative 2 times V1 plus 1 times V2 plus negative 2 times V3. So yes, W can be written as a linear combination of V1, V2, V3. Next example, let V1 equal to 1, 1, V2 equal to 2, 3, V3 equal to 0, 4, and W equal to 2, 5. Let V1, V2, V3, W be vectors in R2. Determine whether W can be written as a linear combination of V1, V2, V3. So try to determine whether W can be written as K1 V1 plus K2 V2 plus K3 V3. If we can find such scalars K1, K2, K3, then that means W can be written as a linear combination of V1, V2, V3. If there does not exist such scalars K1, K2, K3, then we say W cannot be written as a linear combination of V1, V2, V3. So let's try to solve an equation for K1, K2, K3. As we see in the previous example, a shortcut is, in order to find K1, K2, K3, a shortcut is put vectors V1, V2, V3 in the first columns, and then put W in the last column, then reduce the matrices to find K1, K2, K3. So as a shortcut, we put vector V1 in the first column, put vector V2 in the second column, put vector V3 in the third column, and then put W in the last column. Then we can use Gauss-Jordan elimination to solve the matrices for K1, K2, K3. So let's apply Gauss-Jordan elimination. I can first of all multiply first row by negative 1, add it to the second row. I get 1, 2, 0, 2, 0, 1, 4, 3. Next, I can multiply second row by negative 2, add it to the first row. Second row stays the same. 0, 1, 4, 3. 1, 0, negative 8. Negative 2 times 3 is negative 6. Negative 6 plus 2 is negative 4. Which means K3 is a free variable. K3 is a free variable. I get K1 minus AK3 equal to negative 4. So K1 equal to negative 4 plus AK3. K2 plus 4K3 equal to 3. That means K2 equal to 3 minus 4K3. K3 is a free variable. So let K3 equal to T. Let K3 equal to T. We have K1 equal to negative 4 plus AT. K2 equal to 3 minus 4T. 3 minus 4T. K3 itself equal to T. T can be any real numbers. So, since we can find solutions for K1, K2, K3, that means W can be written as a linear combination of V1, V2, V3. So here, let's find one solution. Make it easier. Let T equal to 1. Let's find one solution. Let T equal to 1. Then K1 equal to 4. K2 equal to negative 1. K3 equal to 1. So W can be written as 4V1 minus V2 plus 1V3. So W can be written as a linear combination of V1, V2, V3. Once we find one solution, we can write W as a linear combination of V1, V2, V3. Next example, let A, B, M be vectors in M22. Determine whether M can be written as a linear combination of vectors A and B. So we have to determine whether M can be written as K1 times A plus K2 times B. Here, M is the matrix 0, 1, 2, 0. We try to find K1, K2. If there exist scalars K1, K2, then we say M can be written as a linear combination of A and B. Otherwise, if there does not exist such scalars K1, K2, then we say M cannot be written as a linear combination of A and B. Here, matrix A is 1, 2, 3, 4. Matrix B is negative 1, 2, negative 2, 1. So on the right side, we first of all multiply the scalar to the matrices, and then add the matrices together. If we distribute the scalar, we get K1, 2K1, 3K1, 4K1. The second matrix, if I distribute K2, I get negative K2, 2K2, negative 2K2, and K2. Then when I add the matrices, we add the corresponding components and the corresponding entries. We get K1 minus K2, 2K1 plus 2K2, 3K1 minus 2K2, 4K1 plus K2. That equal to the matrix M, 0, 1, 2, 0, 0, 1, 2, 0. Then, by matching the entries, we get an equation. K1 minus K2 equal to 0. K1 minus K2 equal to 0. 2K1 plus 2K2 equal to 1. 2K1 plus 2K2 equal to 1. 3K1 minus 2K2 equal to 2. 3K1 minus 2K2 equal to 2. 3k1 minus 2k2 equal to 2. 4k1 plus k2 equal to 0. 4k1 plus k2 equal to 0. Then we can write this system of equations as augmented matrix. Next, we can write this system of linear equations as augmented matrix, which is 1, -1, 0, 2, 2, 1, 3, -2, 2, 4, 1, 0. If we observe this matrix, we can see that the first column is the entries in matrix A, 1, 2, 3, 4. The second column is the entries in matrix B, -1, 2, -2, 1, -1, 2, -2, 1. The third column is the entries in matrix M, 0, 1, 2, 0. So for matrices, we can also write it as, for matrices, when we try to find K1, K2, we can also do that. Run the first matrix as a column vector, run the second matrix as a column vector, and write matrix M as a column vector, put it here. Then use Gauss-Jordan elimination, solve these matrices for K1, K2. If there is solutions for K1, K2, then we say M can be written as a linear combination of A and B. Otherwise, if we cannot find solutions for K1, K2, then we say M cannot be written as a linear combination of A and B. So let's reduce the matrices. Here I can first of all multiply first row by -2, add it to the second row. Multiply first row by -2, add it to the second row. You get 0. 2 plus 2 is 4. 0 plus 1 is 1. Next, I can multiply first row by -3, add it to the third row. It's 0. 3 plus -2 is 1. 0 plus 2 is 2. Next, I can multiply first row by -4, add it to the fourth row. I get 0. 4 plus 1 is 5. 0 plus 0 is 0. Next, to make it a little easier, I can divide the last row by 5. I'm trying to make leading one here. In the last row, since we have more zeros here, instead of switching row 2 and row 3, I divide the last row by 5. Make it a little easier. Divide the last row by 5. I have 0, 1, 0. Then interchange row 2 and row 4. Next, interchange row 2 and row 4. First row is 1, -1, 0. Interchange row 2 and row 4. I get 0, 1, 0. 0, 1, 2, 0, 4, 1. Next a leading one. Try to make all entries above and below leading one to be 0. So I can add row 2 to row 1. I get 1, 0, 0. Leave second row the same. Multiply second row by -1, add it to the third row. I get 0, 0, 2. Next, multiply second row by -4. Add it to the fourth row. You get 0, 0, 1. Next, I can interchange row 3 and row 4. Interchange row 3 and row 4. Make leading one here. That's the leading one in the third row. I try to make all entries above and below leading one to be 0. So I can multiply third row by -2, add it to the fourth row. The fourth row becomes 0, 0, 0. So you can see that in the third row, we have 0 equal to 1. That's inconsistent. In the third row, we have 0 equal to 1. We have 0k1 plus 0k2 equal to 1. That's impossible. So this system of equation is inconsistent. So there are no solutions to k1 and k2. So here there are no solutions for k1 and k2. If there are no solutions for k1 and k2, that means M cannot be written as a linear combination of A and B. So matrix M cannot be written as a linear combination of matrix A and B. Next example, let P1 of x be 1 minus 2x plus s squared, P2 of x be 2 minus s squared, and P of x be 4 minus 4x plus s squared. Let P1, P2, and P be vectors in P2, P sub 2. P sub 2 represent the set of all polynomials whose degree is less than or equal to 2. Determine whether P can be written as a linear combination of P1 and P2. So we try to determine whether P of x can be written as K1 times P1x plus K2 times P2 of x. If we can find such scalars K1 and K2, that means P can be written as a linear combination of P1 and P2. On the other hand, if we cannot find such scalars K1 and K2, that means P cannot be written as a linear combination of P1 and P2. So here, P of x is 4 minus 4x plus s squared. P1 of x is 1 minus 2x plus s squared. P2 of x is 2 minus s squared. Let's simplify the right side first. On the right side, I can first of all distribute k1 and k2. I get k1 minus 2k1x plus k1s squared. Second term, I get 2k2 minus k2s squared. Then combine like terms. The constant term is k1 plus 2k2. Then there's only one term of x plus negative 2k1 times x. There are two terms of s squares. Put them together. I have k1 minus k2 s squared. That equal to 4 minus 4x plus s squared. Then for polynomials, we can try to match the coefficient. the constant must be 4. The coefficient of x must be -4. And the coefficient of x squared must be 1. So we have equations. K1 plus 2K2 equal to 4. K1 plus 2K2 equal to 4. Negative 2K1 equal to -4. K1 minus K2 equal to 1. Then we can write this system of equations as an augmented matrix. If I write the system of equations as an augmented matrix, I have 1, 2, and 4 in the first row. -2, 0, -4 in the second row. 1, -1, and 1 in the third row. Now, if we observe these entries, we can see that 1, -2, and 1, those are coefficients of P1. 1, -2, and 1. And 2, 0, -1, those are coefficients of P2. P2 can be written as 2 plus 0x minus 1x squared. 0x is the missing term here. The coefficient is 2, 0, -1. And the coefficient of P is 4, -4, and 1. 4, -4, and 1. Let me match what we have here. So, as a shortcut, we can put the coefficient of P1 in the first column, coefficient of P2 in the second column, and coefficient of P in the last column. That's a quick way to set out a matrix. Put the coefficient of P1 in the first column, coefficient of P2 in the second column, and coefficient of P in the last column. That's a quick way to set out a matrix. Then, solve the matrices for K1, K, and K2. If there is solutions for K1 and K2, that means P of x can be written as a linear combination of P1 and P2. But if there's no solutions for K1 and K2, that means P of x cannot be written as a linear combination of P1 and P2. So let's reduce the matrices. I can first of all multiply first row by 2, add it to the second row. I can first of all multiply first row by 2, add it to the second row. I get 0, 4. A plus -4 is also 4. Next, I can multiply first row by -1, add it to the third row. That's 0. -3 and -3. Next, I can divide the second row by 4. I try to make leading one here. Divide second row by 4. I get 1, 2, 4 in the first row. 0, 1, 1 in the second row. 0, -3, -3 in the third row. Next, in the second row, there's a leading one here. I can multiply second row by -2, add it to the first row. I have 1, 0, 2. Then I can multiply second row by 3, add it to the third row. I get 0, 0, 0, which means K1 equal to 2, K2 equal to 1. If we have solutions for K1 and K2, that means P of x can be written as a linear combination of P1 and P2. So P of x equal to K1 times P1 of x plus K2 times P2 of x. Here I write P of x as a linear combination of P1 and P2. Next example, let f of x equal to 1 g of x equal to sine square of x, and h of x equal to cosine 2x. Let f, g, h be vectors in C. Here, C from net infinity to infinity represent the set of all functions which is continued from net infinity to infinity. Determine whether H can be written as a linear combination of f and g. So we try to determine whether h of x can be written as k1 times f of x plus k2 times g of x. Here, h of x is cosine 2x. F of x is 1. G of x is sine square of x. By double angle formula, we know that since cosine of 2x, by double angle formula, there are 3 formulas. It can be written as cosine square x minus sine square x, or 2 cosine square of x minus 1, or 1 minus 2 sine square of x. Since we try to write cosine 2x in terms of 1 and sine square of x, I can use the last formula. Then cosine of 2x can be written as 1 times 1 plus negative 2 times sine square of x. So by matching the formula here, you can see that k1 equal to 1, k2 equal to negative 2. By matching the double angle formula here, you can see that k1 equal to 1, k2 equal to negative 2. So h of x equal to 1 times f of x minus 2 times g of x. Next, let's create a theorem. Let V be a vector space, and let W1, W2, Wn be vectors in V. Then, the set of all possible linear combinations of W1, W2, Wn form a subspace in V. So here, the theorem says, if W1, W2, Wn they are vectors in V, then the set of all possible linear combinations of W1, W2, Wn form a subspace in V. Let's prove it. So first of all, let W be the set of all possible linear combinations of W1, W2, Wn. Then W can be written as the set of W in V such that W equal to K1 times W1 plus K2 times W2 plus Kn times Wn for all scalars K1, K2, Kn. For all scalars K1, K2, Kn. try to show that W is a subspace of V, which means by earlier theorem, we try to show that W is not empty, W is closed under vector addition, and W is closed under scalar multiplication. First of all, let's try to show that W is not empty. Since 0 times W1 plus 0 times W2 plus 0 times Wn equal to 0, equal to the 0 vector, then 0 vector is a linear combination of W1, W2, Wn. So we can say 0 vector belongs to W. Hence, W is not empty. Since 0 vector equal to 0 times W1, 0 times W2, plus 0 times Wn, so 0 vector is a linear combination of W1, W2, Wn. Therefore, 0 vector belongs to W. Hence, W is not empty. Next, we try to show that W is closed under vector addition. We try to show that W is closed under vector addition. The U and V belong to W. The vectors U and V belong to W. Then, vector U can be written as K1 W1 plus K2 W2 plus Kn Wn. And vector V can be written as, let me use a different letter, L1 W1 plus L2 W2 plus Ln Wn. If I add U and V, we try to show that U plus V also belongs to W. If I add U plus V, what do we get here? U plus V, I have K1 plus L1 times W1 plus K2 plus L2 times W2 plus Kn plus Ln times Wn. Since K and L, the K's and L's are real numbers, when we add real number, we get another real number. So U plus V is also a linear combination of W1, W2, Wn. Therefore, U plus V belongs to W, since W is a set of all possible linear combinations of W1, W2, Wn. Which means W is closed under vector addition. Next, we try to show that W is also closed under scalar multiplication. The U belongs to W, which means U can be written as K1 W1 plus K2 W2 plus Kn Wn. Let K be a scalar. Here, since we use K already, let me use a different letter. Let C be a scalar. In general, we use K, but here, in order to avoid confusion, let me use C. Let C be a scalar. Then, Cu equal to C times K1 W1 plus K2 W2 plus Kn Wn. Because U, vector U is K1 W1, K2 W2, Kn Wn. Then if I distribute C, it can be written as ck1 w1 plus ck2 times w2 plus ckn times wn, which means Cu is also a linear combination of w1, w2, wn. So Cu belongs to W. That means W is closed under scalar multiplication. Since W is non-empty, W is closed under vector addition and scalar multiplication. Therefore, W is a subspace of V. Let's complete the proof of this theorem. So, the set of all linear combinations of these vectors, of any vectors in V, form a subspace in V. Next, let me introduce span. Let V be a vector space, and let S be the set of W1, W2, Wn. Let S be a subset of V. Let W be the set of all possible linear combinations of W1, W2, Wn. Then, by the previous theorem, we know that W is a subspace of V. This subspace W here is called a subspace generated by S. Here, W is called a subspace generated by S, denoted by W equal to span of S, or W equal to span of W1, W2, Wn. And we can also say that vectors W1, W2, Wn span W. Vectors W1, W2, Wn span W. So they all mean the same thing. W equal to span of S. W equal to span of W1, W2, Wn. Or vectors W1, W2, Wn span W. They all mean the same thing. So, based on this definition here, if U can be written as a linear combination of W1, W2, Wn. If U can be written as a linear combination of W1, W2, Wn, that means U belongs to W, since W contains all possible linear combinations. If U can be written as a linear combination of W1, W2, Wn, then U belongs to W. And we know that W is the same as span of W1, W2, Wn. So, if U can be written as a linear combination of W1, W2, Wn, then U belongs to the span of W1, W2, Wn. If U can be written as a linear combination of W1, W2, Wn, then we say U belongs to the span of W1, W2, Wn, because span of W1, W2, Wn is the same as the subspace W. If U cannot be written as a linear combination of W1, W2, Wn, then we say U doesn't belong to the span of W1, W2, Wn. If U can be written as a linear combination of W1, W2, Wn, then U belongs to the span of these vectors. Otherwise, if U cannot be written as a linear combination of these vectors, then U doesn't belong to the span of W1, W2, Wn. In the previous example, we write W as a linear combination of V1, V2, V3. In example 1, we write W as a linear combination of V1, V2, V3. That means W in this example, we can say W belongs to the span of V1, V2, V3. Since I can write W as a linear combination of V1, V2, V3, then we can say W belongs to the span of V1, V2, V3. In example 2, I also write W in terms of V1, V2, V3. Example 2, that's V1, V2, V3, W. Since I write W in terms of V1, V2, V3, In example 2, I can also say that W belongs to the span of V1, V2, V3. In example 3, that's A, B, M. Since M cannot be written as a linear combination of A and B, so we can say that M doesn't belong to the span of A and B. Since M cannot be written as a linear combination of A and B, we say M doesn't belong to the span of A, B. In example 4, since P can be written as a linear combination of P1, P2, since P can be written as a linear combination of P1 and P2, we can also say that P belongs to the span of P1 and P2. In example 4, since I write polynomial P of x as a linear combination of P1 and P2, I can say that P belongs to the span of P1 and P2. Same thing in example 5. Since I write H as a linear combination of F and G, then we can say that H belongs to the span of F and G. Since I write H as a linear combination of F and G, I say H belongs to the span of F and G. So that's what span means. Keep this idea in mind. Next, let's create an example. Let A be a 3 by 3 matrix. Find the solution set of the homogeneous linear system A is equal to 0. According to earlier theorem, we know that if A is an n by n matrix, then the solution set of the homogeneous linear system A is equal to 0 is always a subspace of Rn. Here, A is 3 by 3 matrix. First 3 represent M, second 3 represent N. So, the solution set of this homogeneous linear system must be a subspace of R3. Now, let's find the solution set. First of all, let's set an augmented matrix for this homogeneous linear system A is equal to 0. Let me first of all write A in the front. 1, 2, 4, 0, 2, 3, 1, 0, 1. Then put 0 in the back. That's the augmented matrix of these equations. A is equal to 0. Next, solve this system of equations. Use Gauss-Jordan elimination. I can first of all multiply first row by -1, add it to the third row. I get 1, 2, 4 in the first row. 0, 2, 3 in the second row. 0, -2. -4 plus 1 is -3, 0. Next, I can multiply second row by half, divide second row by 2. I try to make leading one here. Divide second row by 2. I get 1, 2, 4, 0, 0, 1, 3.5, 0, 0, -2, -3, 0. Next, I can multiply second row by -2, add it to the first row. I get 1, 0, 1, 0, 0, 1, 3.5, 0. Then I can multiply second row by 2, add it to the third row. get 0, 0, 0, 0. Which means in the first row we have S1 plus X3 equal to 0. In the second row, S2 plus 3/2 X3 equal to 0. Here, X3 is a free variable. Since there's no leading one in the third column, X3 is a free variable. So I can let X3 equal to T. Then the solution S1, S2, X3 if I solve for S1 here, S1 equal to negative X3, S2 equal to negative 3 over 2 X3. Here, S1 is negative X3, which is negative T. S2 is negative 3 over 2 X3, which is negative 3 over 2 T. X3 is T. The common variable here is T. If I pull out T, I can write it as negative 1, negative 3 over 2, and 1. Yeah, T can be any real numbers. T can be any real numbers. Here you can see that the solution set S1, S2, S3, all solutions can be written as a linear combination of this vector. All solutions can be written as a linear combination of this vector. So the solution set is the span of this vector, negative 1, negative 3/2, and 1. The solution set is span of this vector. Since all solutions can be written as a linear combination of this vector, the solution set is the span of this vector. Next example, let A be a 2×5 matrix. Find the solution set of the homogeneous linear system A is equal to 0. So we first of all set out an augmented matrix. Write matrix A in the front. 1, 2, 3, 4, 1. Negative 1, negative 2, negative 1, 0, and 5. Put 0 in the back. Then use Gauss-Jordan elimination to find the solutions. I can first of all add row 1 to row 2. I get 1, 2, 3, 4, 1, 0 in the first row. 0, 0, 2, 4, 6, 0 in the second row. Next, in the second row, try to make the first non-zero entry to be 1. Here I can divide second row by 2. Keep first row the same. 1, 2, 3, 4, 1, 0. Divide second row by 2. I get 0, 0, 1, 2, 3, 0. Next, try to make 0 here. I can multiply second row by negative 3, add it to the first row. So keep second row the same. 0, 0, 1, 2, 3. Multiply second row by negative 3 added to the first row. I get 1, 2, 0. Negative 6 plus 4 is negative 2. Negative 9 plus 1 is negative 8. 0. So write it back as an equation. I have S1 plus 2S2 minus 4x4 minus 2s4 minus as5 equal to 0. Second equation, I have x3 minus 2s4 plus 2s4 plus 3s5 equal to 0. Then get a leading variable by itself. I get s1 equal to negative 2s2 plus 2s4 plus as5. x3 equal to negative 2s4 minus 3s5. Here, x2, x4, s5, they are free variables. s2, s4, s5, they are free variables. So let x2 be t, let s4 be s, let s5 be r. Then the solution s1, s2, x3, s4, s5. The solution x is a column vector. Write it as s1, s2, x3, s4, s5. Where s1 is negative 2t plus 2s plus ar. x2 is t. x3 is negative 2s minus 3r. s4 is s. s5 is r. That's the solution. Now here in the solution, there are three variables. rst, there are three variables, rst. Write t in the first column. I get negative 2t, t. If there's no t, write 0, 0, 0. Write s in the second column. I get 2s. If there's no s here, write 0. Negative 2s, s, and 0. Write r in the last column. Write r in another column. I get ar, 0, negative 3r, 0, r. Then I can pull out t in the first column, pull out s from second column, pull out r from the third column. If I pull out t, I get negative 2, 1, 0, 0, 0. If I pull out s, I get 2, 0, negative 2, 1, 0. If I pull out r, I get a, 0, negative 3, 0, 1. So you can see that the solution x can be written as a linear combination of these three vectors. The solution x can be written as a linear combination of these three vectors. So the solution set is the span of these three vectors. So the solution set is the span of these three vectors. Negative 2 will write column vector as a vector in vector form. Negative 2, 1, 0, 0, 0. 2, 0, negative 2, 1, 0. A, 0, -3, 0, 1. So the solution set is the span of these three vectors. Since all solutions can be written as a linear combination of these three vectors, the solution set is the span of these three vectors. That's the solution set. That's the solution set of this homogeneous linear system. And we can see that this is a subset of R5. This is a subspace of R5. In the previous problem, this is a subspace of R3. This is a subspace of R5. Next, let me show you some different examples. Let V1, V2, V3 be vectors in R2. Determine whether V1, V2, V3 span R2. We know that if V1, V2, V3 span R2, that means R2 is the set of all possible linear combinations of V1, V2, V3. That means every vector in R2 is a linear combination of V1, V2, V3. So, in order to determine whether V1, V2, V3 span R2, we pick arbitrary element. We first of all pick arbitrary element in R2. Then try to write the arbitrary element as a linear combination of V1, V2, V3. If we can write the arbitrary element as a linear combination of V1, V2, V3, that means V1, V2, V3 span R2. Otherwise, if we cannot write the arbitrary element as a linear combination of V1, V2, V3, that means V1, V2, V3 don't span R2. So, let's first of all pick arbitrary element in R2. Let B equal to B1, B2 belong to R2. That's an arbitrary element in R2. We try to determine whether I can write B as a linear combination of V1, V2, V3. If I can find such scalars K1, K2, K3, that means B is a linear combination of V1, V2, V3. Then V1, V2, V3 spans R2. If we cannot find such scalars K1, K2, K3, that means B cannot be written as a linear combination of V1, V2, V3. That means V1, V2, V3 doesn't span R2. So let's try to solve the equations for K1, K2, K3. So according to the earlier example, we know that a quicker way to set out a system of equations, I can write vector V in the first column, write V1 in the first column, write V2 in the second column, write V3 in the third column, and write B on the last column. Write B on the last column. B is B1, B2. Then use Gauss-Jordan emulation to solve this system of equations. Here I can first of all multiply first row by -1, add it to the second row. Here first row is 1, 2, 0, B1, 0, 1, 4, B2 minus B1. Multiply first row by -1, add it to the second row. Next, I try to make 0 here. So I can multiply second row by -2, add it to the first row. Multiply second row by -2, add it to the first row. First row is B1. Multiply second row by -2. Combine like terms, I get 3B1 minus 2B2. That's the reduced echelon form of this matrix, of this augmented matrix. Here we can see that on each row there's a leading one. Since on each row there's a leading one, then we have solutions for K1 and K2. So the system is consistent. Since there's a leading one on each row, this system of linear equations is consistent. So there are solutions for K1 and K2. There are solutions for K1, K2, and K3. Since there exist solutions for K1, K2, K3, that means B can be written as a linear combination of V1, V2, V3. If an arbitrary element in R2 can be written as a linear combination of V1, V2, V3, that means every element in R2 can be written as a linear combination of V1, V2, V3. That means V1, V2, V3 span R2. Therefore, V1, V2, V3 span R2. On the other hand, if there are no solutions for K1, K2, K3, if it's inconsistent, no solutions for K1, K2, K3, that means V1, V2, V3 don't span R2. Next example, let P1 of x and P2 of x be vectors in P2. Here, this P2 represents a set of all polynomials with degree less than or equal to 2. Determine whether P1 and P2 span P2. So, in order to determine whether P1 and P2 span P2, we first of all pick arbitrary element in P2. If I can write the arbitrary element as a linear combination of P1 and P2, that means these two vectors spans P2. Otherwise, if we cannot write an arbitrary element as a linear combination of P1 and P2, that means P1 and P2 don't span P2. So let's first of all pick arbitrary element in P2. Let P of x be C0 plus C1x plus C2x squared. Let P of x be an arbitrary element in P2. We try to determine whether P of x can be written as a linear combination of P1 and P2. If I can find scalars K1 and K2, that means I can write P of x as a linear combination of P1 and P2. That means P1 and P2 spans P2. Otherwise, if we cannot find scalars K1 and K2, that means this arbitrary vector P of x, cannot be written as a linear combination of P1 and P2. That means P1 and P2 don't span P2. So let's set out the equation first. It's a shortcut. We can write the coefficient of P1 and coefficient of P2 in the first two columns, and write coefficient of P in the last column. Here, coefficient of P1 is 1, -2, and 1. P2 can be written as 2 plus 0x minus s squared. Here, x is a missing term. So coefficient of P2 is 2, 0, -1. Coefficient of P of x is C0, C1, C2. We can try to reduce the matrices, use Gauss-Jordan emulation. If we can find solutions for K1 and K2, that means P1, P2 span P2. Otherwise, P1, P2 doesn't span P2. So I can first of all multiply first row by 2, add it to the second row. I get 1, 2, C0. 0, 4. Two C0 plus C1. Next, I can multiply first row by -1, add it to the third row. I get C2 minus C0. Next, in the second row, try to make leading one here. I can divide second row by 4. First row is 1, 2, C0. Second row is 0, 1. Half of C0 plus a quarter of C1. Leave the third row the same. Next, let the leading one try to make all entries above and below to be 0. Here I can multiply second row by -2, add it to the first row. So I leave the second row the same. 0, 1, half of C0 plus a quarter of C1. So multiply second row by -2, add it to the first row. I get 1, 0. -2 times half of C0. I get C0 plus -2 times half of C0 plus a quarter of C1. Half times -2 times half is -1. -2 times 1/4 is -half. Combine like terms, I get -half of C1. Next, I can multiply second row by 3, add it to the third row. I get 0, 0, 0. 3 times half of C0 plus a quarter of C1 plus C2 minus C0. I get 3/2 of C0 plus 3/4 of C1 plus C2 minus C0. If I combine like terms, I get half of C0 plus 3/4 of C1 plus C2. That's the reduced echelon form of these matrices. Here you can see that since half of C0, 3/4 of C1 plus C2, this is not always 0. Since this is not always 0, we have 0 equal to some non-zero number here. This system of linear equations is inconsistent. So in general, there are no solutions for K1 and K2. Since this is not always 0. So in general, there are no solutions for K1 and K2. Therefore, P of X cannot be written as a linear combination of P1 and P2. Hence, these two vectors, P1 and P2, that they don't span P2. So P of X cannot be written as a linear combination of P1 of X and P2 of X. Therefore, P1, P2, they don't span P2.